webinar here, we're going to basically go over designing intelligible paging systems for emergency communications. It's something we've come across quite frequently lately in regards to a lot of tenders that are coming out now that are requiring either emergency or mass notification paging systems. So there are a few things in there that they've required, and basically we're just going to go over an overview here of how to kind of get started with those, some products that we carry that fall under that category. Okay. So basically we're going to go through an overview here. We're going to do basically semi-volt basics overview. We'll go through speaker ratings and STI, and then we'll do emergency paging with our VM3000 system. So basically, what is semi-volt, a high impedance system? So nowadays, obviously in the professional world, PA, all commercial PA, pretty much everything is all going to be 70 volts. You're not going to get into any low impedance distributed systems for any commercial application. It's pretty much always going to be 70 volt, 25 volt, depending on the scenario you put it in. So basically, these are speakers that are designed for 100 volt, 70 volt, and 25 volt. 100 volts is more common in Europe. Typically here, we run on 70 volt and 25 volt systems. With that, these speakers have adjustable power taps on the speakers. So this is usually done in 3 dB steps. Amplifiers have a high voltage, high impedance outputs, and amplifiers deliver a constant voltage, so changing speaker loads do not affect the speaker volumes connected to the same zone. Again, used mainly for distributed speaker systems comprising of many speakers. So basically, you'll see most common, the speakers itself have different taps on them, and essentially you set the wattage tap depending on what you want to use for that specific application. So, coming on with 70 volts, basically the only limitation we have is wattage. So if we look at this application, 70 volts, always done in parallel wiring. When you do that, basically, and compared to, say, an 8-ohm system, you got to be very careful of your impedance. With 8-ohm systems, you're typically running either a series or a parallel circuit, depending on what kind of impedance you need to go back on the amplifier end. With 70 volt, of course, everything is run 70 volt. Again, our only main limitation would be the wattage. So in this scenario here, if we did 5 speakers at 1 watt each, we only have a 5 watt load. So now you're looking at a scenario where that amplifier can do either a few speakers, it could do 100 speakers, etc. It all depends on what you kind of set your speaker wattage tap to. So what's an advantage when using a high impedance system? So again, all speakers are connected in parallel. There's no series wiring. So no need to maintain a specific impedance load to the amplifier, only a minimum load. So a failure of a speaker or an open speaker transformer will not cause the system to fail, because you could have multiple branches off that to do different parallel runs. And you also have a selection of power taps on each speaker, which allows for level adjustments in different areas. So not only can we have, say, one run of 20 speakers all at 1 watt each, we can have a separate run in parallel branching off the same line or home run that could be at 5 watts each. So adding or removing speakers does not affect the volume levels on existing speakers. We also can do long speaker lines as possible with the appropriate wire gauge. So typically with 70 volt systems, you're looking at, the most common scenario would be an 18 gauge, 16 gauge system. If you use a higher voltage amplifier outputs, that allows you to use smaller wire gauge, and simple wall attenuators can be used to adjust volumes in each zone. So here's a scenario of a typical 70 volt system. You get your BGM, your paging mic, and then you got your runs to your speakers. So there you see one run there. That could be, say for a foyer, first run at 70 volt speakers, and then you have a second run right below that with a wall attenuator, which could be, say, for say a meeting room with your own volume control, and that volume control is only concerned about connecting to those speakers only. That's it. So that volume control only affects those speakers as well. And so some questions before the design. This is typically what you run into when you're doing a design for a 70 volt PA system. So where will the system be used? Will it be indoor-outdoor? Do you need weather-resistant speakers? Is the indoor space high or reverberant? Is there wide dispersion or narrow dispersion speakers? What's the length, width, and height of the room? This is all needed for calculations on our end when we do designs. For swing mount and in-swing, unduct, air return error, is it planar rated? Do we need planar rated speakers, etc.? And then we run into what the system be used for. Is it used just for BGM, foreground music, paging, signaling? This is where we get beyond just a standard PA system and start going into the emergency and or mass notification systems. What are the client's expectations for quality of sound? They need deep bass, and is it used for speech for paging, and what level of intelligibility expected? So you're starting to see now when you get these requirements from customers or on a tender, et cetera. Years ago, just be looking for a public address system, and that comes across on our technical design side of things. Probably every week we get one for a basic PA system, but what we're seeing now is tenders, et cetera, labeled as emergency notification systems. So now there's certain stipulations what they have to follow or certain levels they have to reach or hit in order to do or maintain or be a proper PA system that they're looking for. How loud will it be? Is there ambient noise in the area? Is the system used for foreground material? How will speakers be mounted? Ceiling, wall mount, phone, what kind of brackets you need? Subwoofers are needed? Again, it depends. An emergency PA system, most likely not. But that scenario might be where the subwoofers might be used in a separate area, like an auditorium or a pro AV area. That's part of the whole system. Is there a reference STI level that needs to be achieved? Does the job require a certain level to be achieved in regards to STI ratings? And we'll go over a little bit of STI a little bit later on here. What amplifier power and wiring is required? So amplifier power will depend on the number of power setting of each speaker. Each speaker power tap will depend on the distance from the speaker to the audience. Sound pressure levels are required and ambient noise levels are required. Wire gauge will also come into play. Can we run maybe a large amount of speakers on a thinner wire gauge in order to keep the cost down, et cetera? Do we need DSP processing? Again, depends on the system you're putting in. Some speakers will benefit from like a DSP setup with the 9000 series, the D901 series, et cetera, that will require us to EQ certain speakers for better performance. Is there muting capabilities required? And that comes into play again with emerging communication systems. Pretty much all of them require a muting setup, and that either requires either an external source coming in, external closure coming in, tone coming in, pre-recorded message coming in. So all these things are starting to come into play now where not only do we need to have those priorities set up, we also have to provide either an external source or an external application to do muting. Leveling and compression can be used to maintain a set volume level to basically save or protect the speaker loads on the output side. And again, that's part of our 9000 M2 series, D901 series, and the D2008 series. Do we need multiple amplifier zones? Does the audio system deliver different sound sources in different areas? Is a multi-zone PA system required? So once we branch off to say we want a PA system, that's checked off, we've got our speakers, et cetera, kind of sorted out. We also need to know that we have, say, an emergency PA situation that we have to achieve with priority inputs, et cetera. Maybe they want to do zone paging. That's not only another layer, but something you have to consider whether that product itself will allow you to do zone paging either from a SIP phone system, from an analog phone system, and even from microphones or even an intercom system. What type of sound source is required? Are we doing an all-call paging like a PM660U? Are we doing an analog phone paging system like that with 9000 series with a ZP module? Do we have background music in certain areas or an overall BGM? Again, all these sources will most likely need to be muted in an emergency Evac type of system. We can do pre-recorded messages. We have modules, EV messages systems that will do that for us. So maybe there's not only a separate PA system where a voice is going to do a broadcast, but we also want to have a pre-recorded message that when they hit a, say, emergency push button, it fires off a pre-recorded message to make sure everyone gets out of the building. We could do the same thing with tone modules, a separate tone. They have a pre-recorded tone, or we can have our own module like our S-Series that have built-in tones for you, like a Westminster chime, for example. and we can also have certain modules, depending on what series you go with, to either send a mute signal or receive a mute signal. Control connection to the fire panel is also coming a big topic now of which direction or who has control. So not only will, say, our 9000 series or our VM3000 series allow for a contact closure to come in for emergency mute, we can also send a closure upon a page to do muting as well. So we can either mute or receive a mute towards the fire panel depending on what direction we want to go. So designing a system. So now we have the question of where we start. So sound pressure levels are expressed in dB, decibels. So decibels are used to make a very large numbers easy to manage. So typical dB levels are expressed in the form of 0 dB, which is threshold of hearing, to 140 dB, which is permanent hearing damage. So giving some examples of what those levels mean, you can take a look at the chart here quickly. So 30 dB would be a soft whisper of 5 feet. 50 dB would be a private business office. 70 dB would be an average male voice in a conversation. And then we go up from there. So now you're looking at 90 dB with truck traffic, or even 115 or more dB in a rock concert. So the average listener can hear about a 3 dB change in levels. So the perception that the volume levels have doubled is 10 dB. So ideally, in most scenarios, 10 dB would be the minimum of what you want to be above ambient in order to hear a page, etc. Again, if we go back to the emergency communication side of things, and a lot of tenders we're seeing, those reference points of 10 dB or more above ambient are sometimes 15 to 20 dB more above ambient. So now you're starting to see not only a minimum of what we would perceive as the volume is doubled, they're almost doubling it again just in order to make sure that when they do an emergency page, you're for sure going to hear it. Speaker sensitivity. So this specification indicates how efficient the speaker is producing at producing sound. So all manufacturers measured the speaker on axis at 1 meter distance, referred to reference distance by applying 1 watt of a signal. So when you see a specification of a speaker, it might say 90 dB at 1 watt, 1 meter. So that's just basically the sensitivity that's been rated at that speaker at 1 watt of power going in at 1 meter away. So once you have that information, you can look at the speaker itself, you'll see wattage taps, etc. So how much power to increase the volume levels? So as we've seen, the sensitivity rating tell us that the volume levels in dB, when we use 1 watt of power measured at 1 meter speaker. So when we change that, so basically when perceived, if we have a change of 3 dB, we increase the amplifier power from 1 watt to 2 watt. We're doubling the power basically. So the speaker that produced 9 dB at 1 meter will now produce 93 dB at 1 meter because we've increased the power to that speaker. So every time you double the dB dB rating of that speaker, essentially the power, you increase the dB rating overall. So an example of if we double the power from 1 watt at a 9 dB speaker, we go to 2 watts, we've increased it 3 dB. If we double it again from 2 watts to 4 watts, we go to 96 dB, and so on. So double it again, 4 watts to 8 watts, we're going to 9 dB at 1 meter from the speaker. So this is where you'll get your wattage taps on the speaker to choose whatever wattage tap you want to go with, and now that speaker sensitivity is increased up to what wattage tap you select. So if we chose 8 watt tap on this scenario, our speaker is now rated at 99 dB at 1 meter. And that might sound great. We've gained a 9 whole dB all of a sudden just by changing wattage tap on the speaker. However, we also lose volume of the distance. Now, this is a key thing to keep in mind. Every time you double the distance from the speaker, you actually lose 6 dBs. You're actually using twice as much dB level by increasing the distance. So, keeping that in mind, if we listen to the speaker on axis at 2 meters distance from the sound pressure level, will now be 90 dB minus 6 dB, down to 84 dB. If we move 4 meters away, we double the distance again. So now the volume will be 78 dB. So example in this scenario will be 1 meter, 9 dB, 2 meters, 84 dB, 4 meters, 78 dB. So now, if we keep the sensitivity at 9 dB without changing the wattage tap, every time we double the distance, we're losing 6 dB. So this is something to take in consideration when you're choosing a speaker, that it may be a wide dispersion speaker, for example, but the sensitivity might not be as high as you think it will be. Maybe you want to choose a standard 12-inch baffle, those are generic speakers, but they're only rated at, say, 88 dB sensitivity. But if you chose the same scenario or same type of speaker on that setup, but it's actually rated at, say, 98 dB sensitivity, that's a high-efficient speaker. That may work great in a scenario where you have a high ceiling, you know you're going to be so high that you basically need to hit, say, 4 meters minimum away, so then your dB will drop down depending on that. But keep that in mind. Every time you double the distance, you lose 6 dB. Here's an example. Again, I'll give you a visual example. So SPL, basically 9 dB, 1 meter reference is always going to be just 9 dB, if you don't go away any further than that. If we double the distance of 2 meters, we've dropped down to 84 dB. Double again, we're dropped down to 78 dB. So every time we double the distance, we lose 6 dB. So however, if we kind of offset that by changing wattage taps in this scenario, every time we double the power, we increase 3 dB. So if you look at this scenario here, ear level is roughly 4 meters, 78 dB. We can compensate for that by bringing up the wattage power. So it will take 4 watts of power for the loudspeaker to produce 84 dB at ear level. So in this scenario, if we want to hit at 84 dB, we'd have to increase that speaker to a 5-watt tap minimum based on our distance away from the speaker to kind of make up that compensation in order to hear that properly. So 84 dB might be a perfect point where you need to be at, or an office area where, say, you took an ambient noise level, you're at 70 dB on average, 84 dB would be perfect because you're at minimum 10 dB above for someone to actually know it's a doubling of power. And also, you might hit that second scenario where your emergency communication system says you have to be, say, 10 dB or more above ambience in this setup. We also lose off-axis. So again, these ratings are always basically directly below the speaker itself. So sound pressure levels decrease as they move away from the speaker. The volume levels decrease even more as they move off-axis of the speaker. Obviously, dispersion angles come into play here as well, but speaker manufacturers define the coverage angles based on when the speaker levels off-axis drop 6 dB on-axis response. So suppose the coverage specification for the speaker was 60 degrees horizontal at 2K. So this means that the off-axis volume levels are down 6 dB, 30 degrees each side of on-axis response in the horizontal plane. So not only are we losing dB going straight down, obviously doubling distance, but also off-axis. So keep that in mind when you're doing now your speaker spacing. So another thing you'll find in emergency communications, mass notification tenders, et cetera, not only will they say we must achieve, say, 10, 15, 20 dB above ambient, we also must achieve larger than a 6 dB spread between 6 speakers. So now you could run into a situation where if you put a speaker every 20, 30 feet in a hallway, like you would, say, a standard normal PA system, that might not be enough because your off-axis is actually going to be more than 6 dB from the first speaker to the next speaker. It might be rolling into the 8, 10 dB difference by the time you move into the middle of those two speakers. So that's why you got to make sure your off-axis is covered. So look at this scenario here. If we do our spacing properly, our key goal would be that we don't lose more than 6 dB between speakers. And this is very, very big when you see those mass notification and emergency communication tenders. This is one of probably the most popular thing I've come across when coming across designs is their plus-minus ratio for speaker spacing and what kind of dB they're allowing you to lose in order to do, between your speaker spacing. So Keep that in mind when you see those, and also look out for that type of recommendation or requirement, because those will get you every time if you don't put enough speakers in there and your spacing is going to be way off, and all of a sudden your off-axis coverage now is not basically getting to the level that they want to achieve. Amplifier power is key as well. Since we know in the example we need roughly 84 dB at ear level, we chose a 5-watt tap. We kind of got our room scenario figured out, and we looked at the design, and we calculated that we needed roughly, say, 19 speakers. So when you're designing a 70-volt PA system, you basically take your amount of speakers, and you times it by your wattage tap. So in this example here, we got 19 speakers, 5 watts each. So we're hitting on 95 watts of power required for this setup. Typically, we like to have some headroom in there. That's usually about 20%. So that basically means you must choose an amplifier not only that's going to handle that 95 watts, but you want to be above that by 20% in order to get you some headroom. So in this scenario here, we're looking at 114 watts total. So you basically want to go with a minimum 120 watt amplifier. Now, this could come into play as well as down the future that they want to have maybe possible expansion. Also keep that in mind where they might add an addition to the building, or they want to expand on it later on. Keep that in mind when you're choosing an amplifier and ask those questions. Say, do you plan any maybe expansion in the future? And if they do, then maybe you go with a larger amplifier. Maybe you go with a 240 watt amplifier just to make sure you're safe. So down the line, if they do add any more speakers, you're covered. STI. So STI is becoming very popular nowadays, again, in these emergency evac and mass location tenders. It's starting to basically be mandatory that they need certain STI levels achieved. So STI is basically speech transmission index. It's a measure of how well a person understands the spoken language. It's an objective physical measure of speech transmission quality. So STI values range from 0 to 1, which indicate the degree of which transmission channel degrades speech deniability. So closer to 0 basically means our perception of the spoken word is lost. That we would not understand what words or a sentence would be announced or paid to our PA system. We wouldn't get it. Closer to 1 would be a lot, basically your perfect system. Doesn't matter where you are or what you're doing, you're going to hear that and understand that sentence or word. So intelligibility depends on many factors, such as SPL, ambient noise levels, reverb times, reflections, distortion, et cetera, et cetera. So now you can see when these type of systems, if information or announcements are misunderstood, then tragic consequences can occur. Many of us have been, example, have been in many airports where you hear a page for a flight, you're walking around dragging your suitcase behind you, and you stop. You stop because you're trying to concentrate and listen. Our ears are basically fatigued in this world because we're just so used to hearing things the way we hear them that we don't need to concentrate anymore. Words come naturally to us and we understand them. If we just get part of it, we kind of build it back up in our brain and understand it. But when you come to pages and emergency evac systems, those words need to be understood 100% of the time. So that's why the STI is basically a measurement that they use nowadays that will allow a system to be built and have a certain rating in order to achieve those levels. STIPA is basically a derivative of full STI. It's a measurement tool for speech transmission index for PA systems. I'll give you an idea here of this. Here's kind of how it looks like. You know, you get an announcement, let's play. Here, our environment's fine. We have enough speakers in the building. We're above ambient levels. We have minimum reverb, etc. But in a scenario where we have a large reverberant room, we don't have enough speakers, etc., then we get into a situation where the second example is we don't understand what it's saying, or we can't pinpoint what the words are being announced in that system. So here's an example of a measure. NTI makes a handheld device with their ambient noise mic and a little handheld sensor. Essentially, this will give you a rating, an STI rating of an environment, and when you do a test, it'll give you a rating of a measurement of what that environment or room you're in, et cetera, will be. The reference guide, example of the bottom left there, is pretty much just a generic reference guide. So again, we said 0, close to 0 is pretty much unacceptable, it's horrible. So 0 to 0.3, unacceptable. 0.3 to 0.45 is poor. Once you get into the 0.45 range to 0.6, that's a fair rating that people should basically pretty much understand. And 0.6 and above is pretty much where you want to be at. That's right where you want to be. That's what people are going to understand. And again, that's kind of what's popping up in tenders now. STI ratings, they'll say I have to be at 0.6 and above, et cetera. So that's another thing to look at when you're looking at designing those PA systems, kind of those ratings, you got to make sure you hit them. So how do we go about doing that? Here's the reason. And again, it's going to be more important for job tenders with designs and consultants. Many designs now are requesting that certain STI levels be met within the facility. STI measurements are almost commonly in emergency Evac systems, and the page must be clearly understood in the event of a mass notification message or announcement. So again, this is going back to the tenders that I'm talking about. For a mass notification system, I've seen this example here where, here's an example here, an installation of emergency PA system, mass notification system, et cetera, must obtain an STI level of 0.6 and also must be above 10 dB above ambient with an SPL uniformity of plus or minus 6 dB. So another example will be the target PA SPL level must be at 72 dB. So you'll start seeing these little requirements in these systems where you must hit certain levels. If you don't, you got to put, you got to compensate for that, put more speakers in, et cetera, et cetera. So we know the STI level in this example is 0.6. We know we got to be above 10 dB above ambient. And then uniformity, which is the spacing between speakers, can't drop off more than plus or minus 6 dB. So the target SPL in this scenario is 72 dB. So we got to hit 72 dB minimum in this example and have the rest of those requirements also met in order to be officially approved as a system for this application. So in order to look at that, or to get an example of that, if the building's not built, obviously you'll have no idea how to do this. Or if it's just it's done, but you're asked to put a PA system in, how do you show a client how it's going to perform or how it's going to look? So there's programs out there that you can use, such as Evac, will give you STI levels based on a room. So with this scenario, or with this product, not only can we draw out a room based on like a PDF, CAD drawing, et cetera, we can also input room materials, ambient noise, et cetera, that allow us to simulate what that environment will look like when we add speakers into the room. So there's basic programs out there like our SPV Viewer, which will give you SPL levels in the room. The next level up will be going for like an Evac program where you draw the room out, you add your materials, your wall materials, your floor material, ceiling material, et cetera, and then you plot your speakers out depending on what wattage tap you have. You can also input noise in the background, et cetera, et cetera. So now not only can we do a speaker layout, we can also add in everything we need that will get as close as possible to what that room will look like. So I did a quick example here. Here's a 100 by 10 hallway, 12-foot ceiling. I added drywall for wall and ceiling with a carpet floor. Injected 60 dB ambient noise level. So we say you did a watt test, so you got about 60 dB. And in this installation here, they're looking for STI level of 0.6. It has to be 10 dB above ambient, and SPL uniformity between speakers of no more than plus or minus 6 dB. So with the Evac software, once I built this room up, you can look on the left there as here's my STI levels in this environment. Now this is basically a perfect room essentially. Our STI levels there, we're hitting anywhere from 0.71 above. And as well as if you switch over the SPL reading, you're looking at, we have 72 to 78. So there's our range of plus or minus 6 dB as well. So not only have we hit the STI level that's required, we're hitting the uniformity, which is 72 to 78. There's your 6 dB difference on average, as well as what's the last one, 10 dB above ambient. So we said ambient was 60 dB here, and we're at minimum 72 dB. So there's 3 scenarios that we've hit right off the bat. So what happens if you go into an environment where it's not as ideal? Here's an example here, same room, same level of requirement, et cetera, et cetera. All I changed in this room here was I added a concrete floor. So obviously this is now a lot more reflections going on in this room, and you can see the difference there of just what it drops down to. Keeping pretty good absorbent materials in the wall and ceiling, but now the floor is changed to concrete. So maybe this is like an assembly line or something where it has a concrete floor, hard surface. You can see the difference there. It's just dropped down to 0.49, 0.5, still in the fair range, but obviously a huge difference of how that room performs with the same setup. So go back there, again, perfect room essentially, and there's your room there with a different floor material. So now you can start to see the issues that we run into on the design side of when we get applications where we're given certain room environments and materials, et cetera, where some things don't pan out properly. So how can we improve this? You can add acoustic panels, better materials in the rooms. You've seen paneling, especially for, say, sports facilities like arenas, et cetera. Off in the ceiling, you have a lot of paneling in there to kind of keep the reverberation low. You can add more speakers and lower the wattage taps. Another way to kind of compensate it. Another thing you could try doing would be relocate speakers to where you actually need them. Say it's an open area, you're used to putting pendant speakers in this large open facility, but it's just way too reverberant because you have an open truss ceiling, you got a hard floor, and maybe you have like brick or concrete walls. Maybe you can put the speakers lower on the poles instead and make them more directional. So that's something you can kind of add or remove and do a setup that way where that will improve things and not make the audio go spray everywhere. Obviously, pros and cons are always taken into consideration. As more likely than not, if we were adding more or trying to hit these levels, the cost will increase due to the above changes. I can personally tell you by doing designs where we've met certain criteria and we've put in probably a lot more speakers than we normally would just to meet those criteria. And sometimes that gets denied or not approved, or we're asked to change it because the cost factor goes way up. So those are things to kind of think about, because if you're adding more products, it's going to increase the cost to the end user. And they also have to take into consideration as well, as if they go by what's mandated or what's written in the tender, those type of things might not be 100% met. Maybe you only hit one of the 3 scenarios where you're at the dB level, but your STI may be a bit lower than normal, et cetera. So those are things you got to communicate with them in saying when you do these designs, if you want to hit a perfect system, it might require them to increase the speakers, et cetera, or change amplifiers, et cetera, et cetera. So now, like I said, M&S, ECS, mass notification systems, basically a system used to provide information, instruction to people in buildings or other space using intelligible voice communications like visible signals, text, graphics, tactile, or other communication methods. ECS, Emergency Communication System, is system for protection of life by indicating the existence of an emergency situation and communicating information necessary to facilitate and operate a response or action. So these are the type of words you start seeing in these design requests, and they'll pop up off them now, especially with the new ULCS 576 coming into play soon. So keep an eye out for these, and like I said, when you're doing designs, make sure you note the specific requirements for these and what they're actually looking for. In that regard, looking at the UL, basically the VM3000 is the world's first voice evacuation system compliant with both American and Canadian standards of the UL 2572 and the Canadian ULC S576 listing. Speaking of that unit, this is basically what this unit's features and essentially how it falls into play with the UL S576. So this mixer amplifier essentially allows us to do 240 watts up to 60 zones. We can also add paging mics with zone selection, emergency fire responder mics, and depending how you want to build it up, you can add and have backup power as well to the system. It's got a built-in high-quality digital message repeater, so we have 2 alert and 6 general messages. They can be pre-programmed, or you can submit your WAV file and have your own announcement message. It's programmed via PC software. So any zone setting, priority features, etc., failure detection setting, it's all done by the dedicated PC software. The front panel gives you a display of the current status and configuration, the system setting on the unit, and it basically gives you a sub-menu as well to do any front panel basic setup and identification and programming. So I guess mentioned 240 watts shared over 6 speaker outputs. That's per unit. You can have, say, either one zone at the full 240 watts or have the 240 watts shared over the 6 zones. It's got a speaker attenuator override. Again, that's another key feature in an emergency PA system. If you have a volume control in an office room, all of a sudden they're having a meeting, they turn it off because they don't want to hear any BGM, they don't want to hear any announcements, they don't want to be bothered. Emergency attenuator override will basically override that volume control and broadcast it at full volume regardless of what that setting is. Excuse me. You got 2 remote RM mic inputs. You got your standard 3 mic line inputs for aux inputs for maybe an all-call mic, etc. The 2 BGM inputs, recording out. You have 8 general control inputs/outputs for, say, tie into either a fire panel, push button, an aux input override, whatever you want. We have 6 separate emergency control inputs. Use status output or your CPU failure emergency output, so you can have remote, say, LED panel set up for that. We have a 20-volt DC power port for backup. A main AC power supply, and it's a network connection for just programming and monitoring. It's not actually a network device, but that's how you basically program the unit and monitor it. There's the GUI software essentially for that unit. So you set it up, build it up, depending on how large you want to go. You set up your multiple priorities. You set up your EV messages or your emergency messages at separate higher priority levels. You can build up your zones the way you want it. You can do your all-call the way you want it. And you can add your mics, IDs, etc., all through the software. So it's pretty intuitive. You basically drag and drop to what you want to do. You can enable the surveillance feature as well, which is your speaker line supervision, and monitor the unit itself. And then you can just pick your zones, your events, and how you want the thing to operate, and then essentially you're ready to go from there.